For question 1, my C++ code generated data using the Salmar equation. It was the same for question 2, but we switched wavelength for frequency. For question 2, we used data to plot a graph. It was mostly straight. Deviations were caused by rounding, hence the thin line equation is right as 1 over u plus 1 over v is constant. For question 3, we simulated the light path from A to B via a mirror and plotted the graph, which shows that travel time is minimized when x equals. For question 4, we generated the values and plotted the graphs. This proves Snell's law as a value of x given is also the one predicted by Snell's law. 1a, 1b, 2, 3, and 4. These will plot the graphs for these questions.
For question 5, this code takes in an image into a 3D array and loops over each non-transparent pixel to center, scale, and shift them. We then mirror every point by training all of the corresponding values in C negative. Question 6, we define our initial focal length, distance, and height. We then plot the focal points in an object. We use the lens formula and prepare our rays, which are initially empty and are updated later with the sliders. For question 7, we calculate the initial image properties like distance, plot the lens, points, and the relevant rays, like the one parallel to axis. For question 8, this calculates x coordinates for given y ones, and we also find the reflected vector. This distorted image works by calculating the squared radius from the center for each pixel and applying distortion and magnification. For question 9, we define the initial optical parameters, and we use the sin mirror formula for image distance and magnification. We also draw the relevant rays in images. For
Question 10, Python uses NumPy to warp the image into cylindrical coordinates. This demonstrates distortion in curve reflection. For 11a, using refraction formulas, Python plots a graph showing elevation vs incidence angle. Python plots elevation vs frequency, showing how primary and secondary rainbows depend on light frequencies. For 11c, Python shows a graph of refraction angles of different wavelengths of light. By using a quadratic, it estimates the values. For 11d, Python generates a circle, and as the solar angle increases, the circle goes down but also increases in size, creating the view you will see. For 12a, Python simulates a rays parting a triangular prism by using Snell's law of refraction. For question 12b, graph 1 plots a graph of transmission angle vs incidence angle, showing how Snell's law works. 12b graph 2 shows how the total deflection angle of a light ray changes when it enters a prism. 12b graph 3 shows how it depends on the wavelength of the light. Here are graphs.
Graphs for question 5, 6, 7, 8, and 9. So we made a data synthesizer and a machine learning regression model to predict the location of a ray on the screen after reflecting off a concave mirror from different positions, angles, and focal lengths, etc. It has a mean error of only 4%, as you can see here.